close your eyes and descend into the deep. Tonight, we journey beneath the waves, to a world of endless blue, glowing creatures, and mysteries hidden in the darkest depths. The ocean covers 70% of our planet, yet we have explored less than 5% of its waters. Let these stories of the deep carry you into peaceful sleep. This is Nightly Lore. The ocean is divided into 5 distinct zones, based on depth and light penetration, each hosting entirely different forms of life adapted to extreme conditions. Scientists organize these zones according to how far sunlight can reach, and how much pressure exists at each level. Near the surface, where light is abundant, life bursts with color and activity. Fish dart through coral reefs, dolphins leap through waves, and seabirds dive for their meals. But as you descend deeper, the world transforms. Light fades gradually, temperatures drop, and pressure builds with every meter. The creatures that live in each zone have evolved remarkable adaptations to survive in their particular layer of the ocean. Some have enormous eyes to capture every available photon of light. Others have given up on sight entirely, relying instead on smell, vibration, or bioluminescence to navigate the darkness. Each zone operates like a separate world, with its own rules, its own rhythms, and its own forms of life that would struggle to survive anywhere else in the ocean. The sunlight zone, or epipelagic zone, extends from the surface down to about 200 meters, where enough light penetrates for photosynthesis to occur. This is the layer of the ocean most familiar to humans. When you swim at the beach, snorkel over a reef, or watch dolphins from a boat, you are observing life in the sunlight zone. Here, light filters down through the water in shifting patterns, creating dancing shadows on the sandy bottom. Phytoplankton, microscopic plants, too small to see individually, drift in vast numbers near the surface. They form the foundation of the ocean food web, using sunlight to create energy through photosynthesis, just like plants on land. Small fish gather to feed on these clouds of plankton. Larger fish arrive to hunt the smaller ones. Seals, sea lions, and dolphins patrol these waters. Sea turtles glide peacefully through kelp forests. The sunlight zone is warm, bright, and filled with life in constant motion, a stark contrast to the still cold darkness that waits below. Below the sunlight zone lies the twilight zone, or mesopelagic zone, reaching down to 1,000 meters, where only faint blue light filters through from above. The transition between the sunlight and twilight zones is gradual, not sudden. As you descend, colors begin to disappear one by one. Red fades first, absorbed by the water within just a few meters of the surface. Then orange and yellow vanish. By the time you reach 100 meters down, only blue-green light remains, and even that grows dimmer with every meter. At 200 meters, the boundary of the twilight zone, the light becomes so faint that photosynthesis is no longer possible. Yet it is not completely dark. A ghostly blue glow persists, barely enough to see by, creating an eerie half-world between day and night. The creatures here have learned to live in this perpetual dusk. Many possess large, sensitive eyes. Others have developed bioluminescence, creating their own light in the gloom. The twilight zone is a place of transition, caught between two very different worlds. The midnight zone, called the bathypelagic zone, stretches from 1,000 to 4,000 meters deep, in complete and permanent darkness. No trace of sunlight reaches this depth. The last faint glow of blue from the surface fades completely around 1,000 meters down, leaving absolute blackness. For a human visiting this zone in a submarine, the darkness is total and disorienting. Outside the submarine's lights, there is nothing, no up or down, no sense of space or distance, just endless black void. Yet this darkness is not empty. Life persists here in remarkable forms. Fish with enormous mouths and expandable stomachs drift slowly through the water, conserving energy in an environment where food is scarce. Bioluminescent creatures create brief flashes of light, like fireflies in a summer field, but scattered through three-dimensional space. The midnight zone is vast, covering more area than all the continents combined. It is cold, dark, and under immense pressure. Yet life has found ways not just to survive but to thrive in these extreme conditions. The abyssal zone extends from 4,000 to 6,000 meters deep, covering vast plains of the ocean floor in crushing pressure and near freezing temperatures. This is a realm of mud and sediment, stretching for thousands of kilometers in gentle rolling plains. The pressure here is so intense that it would instantly crush any air-filled cavity. A styrofoam cup lowered to this depth would compress to the size of a thimble. The temperature hovers just above freezing, between 2 and 4 degrees Celsius, year-round. No seasons exist at this depth. No weather, no day or night, just constant, unchanging cold and darkness. The abyssal plains are covered in soft sediment that has drifted down from the surface over millions of years. This sediment, called marine snow, is made of dead organisms, fecal matter, and tiny particles that fall like an endless, gentle rain from the waters above. Despite the harsh conditions, life exists here. Sea cucumbers crawl along the bottom, processing sediment for any organic material. Brittle stars wave their arms in the current, filtering food particles from the water. The deepest zone, the hadal zone, exists in ocean trenches deeper than 6,000 meters, reaching down nearly 11,000 meters in the Mariana Trench. This zone is named after Hades, the Greek god of the underworld, because it represents the deepest, most extreme environment on Earth. Ocean trenches form where one tectonic plate slides beneath another, creating long, narrow depressions in the ocean floor. The Mariana Trench, located in the western Pacific Ocean, contains the deepest known point on Earth, called Challenger Deep. At nearly 11,000 meters down, the pressure at Challenger Deep exceeds 1,000 times the atmospheric pressure at sea level. For decades, scientists believed nothing could live at such depths. The pressure, the cold, the complete absence of light all seemed too extreme for life. But they were wrong. When explorers finally descended to the bottom of the Mariana Trench, they found life. Small amphipods, shrimp-like creatures, scuttled across the sediment. Fish swam past the submarine's windows. Even at the very bottom of the ocean, life persists. Pressure at the bottom of the Mariana Trench exceeds 8 tons per square inch, enough to crush most submarines designed for deep exploration. To understand this pressure, consider that at sea level, the atmosphere exerts about 15 pounds per square inch on your body. Why? Oh, you do not notice this, because the pressure inside your body equals the pressure outside. But water is much heavier than air. With every 10 meters you descend in the ocean, the pressure increases by 1 atmosphere. At 100 meters, the pressure is 11 atmospheres. At 1,000 meters, it is 101 atmospheres. At the bottom of the Mariana Trench, the pressure reaches over 1,000 atmospheres, or about 8 tons, pressing down on every square inch. This pressure would instantly collapse your lungs, crush your skull, and compress your body to a fraction of its normal size. Only a handful of specially designed submersibles can withstand such pressure. These vessels have thick titanium walls, reinforced viewports, and carefully engineered systems to keep their human occupants alive. Even with this technology, descending to the deepest parts of the ocean remains one of the most dangerous and difficult journeys humans can make. Despite this crushing pressure, Life thrives even in the deepest trenches, including fish, shrimp, and microorganisms, specially adapted to extreme environments. The creatures living at these depths have evolved remarkable adaptations. Their bodies contain no air spaces that could be crushed by pressure. Their cells are filled with special molecules that help them resist the crushing force of the water. Some deep-sea fish have soft, gelatinous bodies with flexible bones that can withstand the pressure. Others have proteins in their cells that remain stable and functional even under extreme compression. Microorganisms at these depths possess unique enzymes that work at high pressure and low temperature, conditions that would cause most proteins to denature and stop functioning. These adaptations took millions of years to evolve. The creatures of the hadal zone are not visiting from shallower waters. They live their entire lives in this extreme environment, perfectly suited to conditions that would kill most other organisms within seconds. Their existence reminds us that life, once established, can adapt to nearly any environment Earth has to offer. Water temperature in the deep ocean remains just above freezing, hovering around 2 to 4 degrees Celsius throughout the year. This cold is constant and unchanging, while surface waters warm in summer and cool in winter. While tropical seas stay warm and polar seas freeze solid, the deep ocean maintains its steady chill. The cold water sinks because it is denser than warm water, a process that helps drive ocean currents. At the poles, cold surface water becomes even colder and saltier as sea ice forms, leaving the salt behind. This cold, salty water is the densest water in the ocean, and it sinks all the way to the bottom, then spreads slowly across the abyssal plains. This process, called thermaline circulation, creates a slow but constant flow of cold water through the deep ocean. The cold affects everything living at these depths. Cold-blooded creatures which cannot generate their own body heat move slowly to conserve energy. Their metabolisms run at a fraction of the speed of their warm water cousins. They grow slowly, reproduce slowly, and can live for decades or even centuries. The deep ocean is remarkably silent compared to the surface, with most sound coming from the slow movements of currents and the calls of whales traveling vast distances. At the surface, waves crash, wind howls, rain patters, and boats rumble past. But descend a few hundred meters, and most of these sounds fade away. The surface of the ocean acts like a barrier, absorbing and reflecting sound. In the deep ocean, away from shore and shipping lanes, the water becomes eerily quiet. You might hear the occasional creak and groan of a submarine's hull adjusting to pressure. You might hear the hum of the submarine's engines. But outside, in the water itself, silence dominates. The most common sounds are subtle. The faint rustle of sediment settling on the ocean floor. The barely audible movement of deep currents flowing past underwater mountains. And then, cutting through the silence, come the calls of whales. Whale songs can travel for hundreds or even thousands of kilometers through the deep ocean, using a layer of water called the Sofar Channel, where sound waves can travel with minimal loss. Ocean currents move in slow, predictable patterns called thermaline circulation, driven by differences in temperature and salinity rather than wind. Unlike the surface currents that sailors have used for centuries, which are driven primarily by wind, deep ocean currents move because of differences in water density. Cold water is denser than warm water. Salty water is denser than fresh water. The coldest, saltiest water is the densest of all, and it sinks to the bottom of the ocean. This dense water forms near the poles, particularly around Antarctica, and in the North Atlantic near Greenland. Once it sinks, it begins a slow journey across the ocean floor. This deep water creeps along at a pace of only a few centimeters per second, far slower than any surface current. It flows along the contours of the ocean floor, following underwater valleys and squeezing through gaps between underwater mountains. The current carries oxygen and nutrients from the surface into the deep ocean, sustaining life in regions that would otherwise be devoid of these essential elements. These deep currents can take 1,000 years to complete a full circuit around the globe, carrying nutrients and oxygen to the deepest parts of the ocean. This vast, slow-moving conveyor belt is sometimes called the global ocean conveyor, or the thermaline circulation. Water that sinks near Greenland today might not return to the surface until the year 3000. During its journey, this water flows south along the bottom of the Atlantic Ocean, past the equator, around the southern tip of Africa, and into the Indian and Pacific Oceans. Eventually, in certain regions, this deep water rises back toward the surface, in a process called upwelling. When it rises, it brings with it nutrients that have accumulated during its long journey through the deep. These nutrients fertilize surface waters, supporting blooms of phytoplankton that feed fish, which feed larger fish, which feed marine mammals and seabirds. The entire ocean ecosystem depends on this slow circulation. This exchange between surface and depth, that takes centuries to complete, but sustains life throughout the sea. The ocean floor is not flat but contains mountain ranges, volcanoes, and trenches that rival any geological features found on land. For most of human history, people imagined the ocean floor as a vast, featureless plain of mud. But modern sonar mapping has revealed a landscape as varied and dramatic as any continent. Underwater mountain ranges, called mid-ocean ridges, stretch for thousands of kilometers across the ocean floor. These ridges mark the boundaries where tectonic plates pull apart, and new ocean floor forms from molten rock rising from below. Underwater volcanoes, called seamounts, rise from the abyssal plains, some reaching heights of several thousand meters. A few break the surface to form volcanic islands like Hawaii. Deep ocean trenches plunge down to depths of over 10,000 meters, forming the deepest parts of the ocean. The ocean floor also contains vast underwater plateaus, steep cliffs, and winding canyons carved by underwater avalanches of sediment. If you could drain the ocean, the revealed landscape would be more dramatic than any range of mountains or any desert canyon on land. The Mid-Atlantic Ridge, an underwater mountain range, runs down the center of the Atlantic Ocean and is where new ocean floor is constantly being formed. This ridge stretches from the Arctic Ocean to near the southern tip of Africa, a distance of over 16,000 kilometers. It marks the boundary between the North American and Eurasian plates in the north, and the South American and African plates in the south. Here, the tectonic plates are pulling apart at a rate of about 2.5 centimeters per year, roughly the rate your fingernails grow. As the plates separate, molten rock from the Earth's mantle rises to fill the gap. This molten rock, called magma, cools when it contacts the cold ocean water, solidifying into new ocean floor. This process, called seafloor spreading, creates new crust continuously. The ridge itself rises 2 to 3 kilometers above the surrounding ocean floor, with a rift valley running down its center where the newest rock forms. Hydrothermal vents cluster along the ridge, supporting unique ecosystems. The Mid-Atlantic Ridge is one of the most geologically active features on Earth. Hydrothermal vents, discovered only in the 1970s, spew superheated water from beneath the ocean floor, creating unique ecosystems around them. Before their discovery, scientists believed that all life on Earth ultimately depended on sunlight. Plants use sunlight to create energy through photosynthesis, and all other life feeds on plants or on animals that eat plants. But hydrothermal vents proved this assumption wrong. These vents occur where seawater seeps down through cracks in the ocean floor, gets heated by molten rock below, and then erupts back out into the ocean at temperatures that can exceed 400 degrees Celsius. The water is so hot it would instantly boil at the surface, but the immense pressure at depth keeps it liquid. The superheated water carries dissolved minerals and chemicals from deep within the earth. When this hot, chemical-rich water meets the cold ocean water, minerals precipitate out, forming chimneys that can grow several meters tall. Around these vents, bacteria harvest energy, not from sunlight but from chemicals in the vent water, particularly hydrogen sulfide. These bacteria form the base of an entire ecosystem, supporting tube worms, clams, crabs, and fish in the complete darkness of the deep ocean. Bioluminescence is the production and emission of light by living organisms through chemical reactions within their bodies. Unlike light bulbs or fires that produce light through heat, bioluminescence is a cold light, generated by a chemical process that releases energy in the form of photons rather than heat. This remarkable ability has evolved independently in many different groups of organisms, from bacteria to fish, from jellyfish to squid. Each species has developed its own unique system for producing light, though the basic chemistry remains similar across different lineages. The light can be steady or flashing, bright or dim, localized to specific organs, or spread across the entire body. Some creatures glow continuously from birth to death. Others activate their light only when needed, switching it on and off with precise control. For organisms living in the perpetual darkness of the deep ocean, bioluminescence serves as their primary means of communication, defense, and hunting. It transforms the midnight zone into a realm of flickering lights, brief flashes, and glowing trails, creating an alien landscape of living stars scattered through three-dimensional space. Scientists estimate that up to 90% of creatures living in the deep ocean possess some form of bioluminescence. This staggering percentage reveals just how important light production is for survival in the deep sea. In a world without sunlight, the ability to create your own light provides enormous advantages. You can attract prey with a glowing lure. You can startle predators with a sudden flash, giving you precious seconds to escape. You can signal to potential mates, advertising your presence in the vast darkness. You can even camouflage yourself by matching the faint downwelling light from above, making your silhouette invisible to predators hunting from below. The prevalence of bioluminescence in the deep ocean stands in stark contrast to life on land, where bioluminescence is relatively rare, limited mainly to fireflies, some fungi, and a handful of other organisms. In the ocean's depths, bioluminescence is not an unusual trait but the norm. A creature without the ability to produce light is at a severe disadvantage, struggling to find food, avoid predators, and locate mates in an environment where darkness is absolute and permanent. The light is produced when a chemical called luciferin reacts with oxygen in the presence of an enzyme called luciferase. This chemical reaction is remarkably efficient at converting chemical energy into light energy. While an incandescent light bulb wastes most of its energy as heat, with only about 5% emerging as visible light, bioluminescence can achieve up to 90% efficiency. Nearly all the energy goes into producing light rather than heat. The specific type of luciferin varies between different groups of organisms. Fireflies use one type, marine bacteria use another, and deep-sea fish use yet another. But the basic principle remains the same. Luciferin molecules, when combined with oxygen in the presence of the luciferase enzyme, enter an excited state, and then release energy as photons when they return to their ground state. The organism controls when this reaction occurs by regulating the supply of oxygen or luciferin to the light-producing cells. This allows for precise timing of flashes and complete control over when to glow and when to remain dark. Different species produce different colors of bioluminescent light, though blue and green are most common because they travel farthest through water. Water absorbs different wavelengths of light at different rates. Red light is absorbed quickly, disappearing within the first few meters below the surface. Orange and yellow follow soon after. Blue and green light penetrate deepest, which is why the ocean appears blue when viewed from above, and why the faint light in the twilight zone has a blue-green hue. Organisms producing bioluminescence have evolved to emit wavelengths that travel efficiently through their environment. Most deep-sea creatures produce blue or blue-green light, maximizing the distance their signals can travel. Some organisms, however, have evolved to produce red light. Since most deep-sea creatures cannot see red wavelengths, having lost that ability because red light never reaches their habitat naturally, a red bioluminescent beam acts like an invisible searchlight. The predator can see prey illuminated by this red light, but the prey, unable to detect red wavelengths, remains unaware it is being observed. Some organisms can control their bioluminescence, turning it on and off at will, while others glow continuously. The ability to control bioluminescence requires sophisticated biological machinery. Specialized cells called photophores contain the light-producing chemicals and often include reflectors, lenses, and filters to direct and modify the light. The organism can trigger light production by releasing luciferin into a chamber containing oxygen and luciferase, or by controlling oxygen delivery to cells that already contain both chemicals. Some species can create complex flashing patterns, with different groups of photophores firing in sequence to create waves of light across their bodies. This level of control requires a nervous system capable of precise timing and coordination. Other organisms use a simpler system where bacteria living in specialized organs produce light continuously. The host controls this light not by turning the bacteria on and off, but by covering and uncovering the light organs using pigmented screens, similar to how you might control a flashlight by covering it with your hand. Both strategies work effectively in the deep ocean's darkness. Bioluminescence serves many purposes, including attracting prey, communicating with others of the same species, and startling or confusing predators. In the competition for survival in the deep ocean, light becomes a versatile tool. A predator can use a glowing lure to attract curious prey within striking distance, essentially fishing with light in the darkness. Many species use specific flashing patterns to identify and attract mates, with each species having its own unique signal, like a Morse code of light that prevents confusion between similar-looking species. When threatened, some creatures release a cloud of glowing chemicals into the water, creating a decoy that distracts the predator, while the prey escapes into the darkness. Others create sudden bright flashes that startle predators, causing them to hesitate just long enough for escape. Some species use bioluminescence for camouflage through a technique called chetoillumination, where light organs on their bellies produce a glow that matches the faint downwelling light from above, erasing their silhouette when viewed from below. Each of these strategies represents a sophisticated use of light in an environment where light is scarce and precious. The anglerfish uses a bioluminescent lure dangling in front of its mouth to attract smaller fish in the pitch-black depths. The female anglerfish, much larger than the tiny male of the species, possesses a modified dorsal fin spine that extends forward over her head like a fishing rod. At the tip of this rod dangles a fleshy bulb called an esca, which glows with bioluminescence produced by symbiotic bacteria living inside. In the complete darkness of the deep ocean, this glowing lure is irresistible to smaller fish and invertebrates. They approach, curious about this mysterious light source, and come close enough for the anglerfish to strike. The anglerfish has an enormous mouth lined with long needle-like teeth that angle inward, making escape nearly impossible once prey is seized. Her stomach can expand to accommodate prey almost as large as herself, an important adaptation in an environment where meals are few and far between. The anglerfish remains nearly motionless while hunting, conserving energy and waiting patiently for prey to investigate her glowing lure. This passive hunting strategy requires minimal energy expenditure, while maximizing the chance of a successful catch. Some squid species can produce flashing patterns of light across their bodies, possibly to communicate or to camouflage themselves against the faint light from above. These squid possess hundreds or even thousands of photophores distributed across their skin in complex patterns. By controlling which photophores glow and which remain dark, the squid can create dynamic displays of light that ripple across their bodies in waves or flash in specific sequences. Some researchers believe these patterns serve as a form of communication, allowing squid to signal to each other in the darkness. Different patterns might convey different messages, such as warnings about predators, signals of aggression, or invitations to mate. Other scientists suggest the primary function is camouflage. By carefully matching the intensity and pattern of their belly lights to the faint downwelling light from the surface, the squid can make their silhouette disappear when viewed from below. Predators hunting from the depths would see only uniform light, with no shadow to betray the squid's presence. Whatever the exact purpose, the ability to create these complex light displays represents a remarkable evolutionary achievement. The cookie-cutter shark has bioluminescent organs on its belly that help it blend in with the faint light filtering down from the surface, making it invisible to prey below. This small shark, rarely exceeding half a meter in length, has evolved an unusual hunting strategy. Its belly is covered with photophores that glow with a steady light matching the intensity of the downwelling light from above. When prey looks up from below, the shark's silhouette disappears against the background light. However, the shark has one dark patch near its throat that does not glow. This dark spot might resemble a small fish when viewed from below, attracting larger predators upward to investigate. When the predator approaches, the cookie-cutter shark strikes, using its specialized teeth to remove a circular plug of flesh before swimming away. This technique allows the small shark to feed on prey much larger than itself, including tuna, marlin, dolphins, and even whales. The distinctive circular scars left by cookie-cutter sharks can be found on many large marine animals, evidence of these nighttime ambush attacks in the deep ocean. Jellyfish produce some of the most spectacular bioluminescent displays, with some species creating cascades of blue-green light when disturbed. Unlike fish or squid that have concentrated light organs, many jellyfish distribute light-producing cells throughout their bodies, particularly along the edges of their bells and down their tentacles. When something touches a jellyfish or disturbs the water around it, the mechanical stimulation triggers the bioluminescent reaction. Light races across the jellyfish in waves, outlining its entire body in glowing blue-green. This sudden burst of light might startle a predator, causing it to release the jellyfish. It might also attract larger predators to the area, which might then attack whatever disturbed the jellyfish in the first place, allowing the jellyfish to escape in the confusion. Some jellyfish produce brief flashes, while others can maintain a steady glow for several seconds or even minutes. When disturbed, a group of jellyfish might create a coordinated light show, with waves of bioluminescence passing from one individual to another, creating an underwater aurora of living light in the darkness. Dinoflagellates, microscopic organisms, create the glowing waves seen along some beaches at night when waves or movement disturb them. These single-celled organisms are so small that you cannot see them individually without a microscope. Yet they exist in such enormous numbers that they can turn entire bays into glowing seas of light. When conditions are right with warm water and abundant nutrients, dinoflagellates bloom, multiplying until they number in the millions per liter of water. During the day, these blooms might color the water reddish-brown, an event sometimes called a red tide. At night, when waves crash or a swimmer moves through the water, the mechanical disturbance triggers the dinoflagellates' bioluminescence. Each organism produces a tiny flash of blue-green light that lasts only a fraction of a second. But when millions of dinoflagellates flash simultaneously, the effect is magical. Breaking waves glow blue. Footprints on wet sand sparkle with light. A hand dragged through the water leaves a glowing trail. This bioluminescence might serve as a defense mechanism, with the sudden light startling small predators, or attracting larger predators that might eat whatever disturbed the dinoflagellates. A single cup of ocean water can contain millions of these bioluminescent dinoflagellates, though they are invisible to the naked eye during the day. The sheer abundance of these microscopic organisms is difficult to comprehend. In a dense bloom, each liter of water might contain 10 million dinoflagellates or more. They drift with currents, unable to swim strongly against the ocean's movements, forming vast clouds of living cells that can extend for kilometers. Each dinoflagellate is a complete organism, capable of photosynthesis during the day, using the energy of sunlight to create food, and producing bioluminescence at night when disturbed. They possess tiny whip-like tails called flagella that they use for weak swimming, mostly to maintain their position in the water column rather than to travel. During daylight hours, you would never know they were there unless you examined a water sample under a microscope. They appear as tiny specks, geometric in shape, some with ornate coverings of cellulose plates. Only at night, when disturbed, does their presence become obvious through the ghostly blue glow they collectively produce. The firefly squid, found off the coast of Japan, produces blue light from organs all over its body, and gathers in massive glowing swarms during mating season. These small squid, only about 7 centimeters long, possess photophores distributed across their tentacles, around their eyes, and throughout their bodies. They can control each photophore independently, creating complex patterns of light that flash and pulse across their skin. During the day, firefly squid live at depths of 200 to 400 meters, rising toward the surface at night to feed on small fish and plankton. But during spawning season, which occurs from March to May, they gather in massive numbers in Toyama Bay on Japan's western coast. Thousands upon thousands of squid congregate, and from the shore, the water appears to glow with an eerie blue light. Fishermen have harvested these squid for centuries, and the spectacle now attracts tourists from around the world who come to witness the glowing waters. After mating, the squid die, their life cycle complete, but not before creating one of nature's most spectacular light shows. Some species of fish have bioluminescent bacteria living in special organs, creating a symbiotic relationship where the bacteria produce light in exchange for nutrients. This arrangement benefits both partners. The fish provides the bacteria with a safe home, a steady supply of nutrients, and oxygen. In return, the bacteria produce light that the fish can use for hunting, communication, or camouflage. The light organs that house these bacteria can be remarkably complex structures. They might include reflective layers to direct the light, lenses to focus it, and pigmented shutters to control when light is visible. Some fish can even adjust the intensity of the bacterial glow by controlling oxygen delivery to the light organ. The bacteria themselves are usually species that specialize in this symbiotic lifestyle, often unable to survive long outside their host. When a fish is born, it typically does not yet have its bacterial partners. Young fish must acquire the bacteria from the environment, and the correct bacterial species must find and colonize the developing light organs. Once established, this partnership lasts for the fish's entire life, the bacteria passing from generation to generation. Scientists have only recently begun to understand how widespread bioluminescence is, with new glowing species discovered regularly during deep-sea explorations. For most of human history, the deep ocean was completely inaccessible. We could only imagine what lived in the dark waters far below the surface. The development of deep-sea submersibles and remotely operated vehicles changed everything, allowing scientists to descend into the midnight zone and observe its inhabitants in their natural habitat for the first time. What they found astonished them. Bioluminescence was not rare, but commonplace. Not an unusual adaptation, but the standard. Nearly every expedition into the deep returns with observations of previously unknown bioluminescent organisms, or new behaviors of known species. Jellyfish that produce light in colors never before documented. Fish with light organs in unexpected locations. Squid creating patterns of light more complex than anyone had imagined. Each discovery reveals new facets of how life has adapted to create and use light in the ocean's perpetual darkness. The study of bioluminescence continues to surprise researchers, suggesting that much about this phenomenon remains to be learned. The giant squid, once thought to be a myth, can grow up to 13 meters long and lives at depths of 300 to 1,000 meters. For centuries, sailors told stories of enormous sea monsters with tentacles long enough to drag ships beneath the waves. These tales were dismissed as exaggeration or fantasy, the product of long months at sea and too much rum. But the sailors were describing something real. Giant squid do exist, though they are not quite the ship-destroying monsters of legend. They are, however, genuinely enormous, among the largest invertebrates on Earth. A full-grown giant squid can reach 13 meters from the tip of its body to the end of its longest tentacles, and weigh up to 300 kilograms. For most of history, the only evidence of their existence came from dead specimens that washed ashore, or were found in the stomachs of sperm whales. Scientists had never observed a living giant squid in its natural habitat. That changed only in the early 2000s, when researchers finally captured the first footage of a giant squid swimming freely in the deep ocean, confirming that these creatures of legend were indeed real. Giant squid have the largest eyes in the animal kingdom, up to 30 centimeters in diameter, perfectly adapted for detecting faint light in the deep ocean. Each eye is roughly the size of a dinner plate, an enormous organ relative to the squid's body size. These massive eyes serve a critical purpose in the dim twilight zone where giant squid hunts. At depths of 300 to 1,000 meters, very little light penetrates from the surface, but the faint glow that does exist can be detected by sufficiently large and sensitive eyes. The giant squid's eyes are optimized for gathering every available photon of light. They have large lenses, wide pupils, and retinas packed with light-sensitive cells. This visual system allows the squid to detect the silhouettes of prey, swimming above them against the faint downwelling light from the surface. The eyes might also help detect bioluminescence, either from prey or from predators approaching in the darkness. The size of these eyes has fascinated biologists for years. Why evolve such enormous eyes when smaller ones would seem sufficient? The answer likely relates to detecting sperm whales, the giant squid's primary predator, at the greatest possible distance in the low light conditions of the deep ocean. The colossal squid, even larger than the giant squid, possesses hooks on its tentacles and lives in the deep waters around Antarctica. While the giant squid captures imagination, the colossal squid truly earns the title of largest invertebrate. Specimens have been found with bodies, excluding tentacles, measuring up to 4 meters long, and total lengths including tentacles estimated at up to 14 meters. The colossal squid is also heavier, with more massive bodies than giant squid, potentially weighing up to 700 kilograms. What truly sets the colossal squid apart, however, are its arms and tentacles. While giant squid have suckers lined with small teeth, colossal squid possess sharp, swiveling hooks among their suckers. These hooks can rotate and are strong enough to penetrate flesh, making them formidable weapons for capturing prey and defending against predators. The colossal squid inhabits the deep, cold waters surrounding Antarctica, living at depths of up to 2,000 meters. Very few specimens have been studied, most found dead or dying after being caught accidentally by fishing vessels. Each new specimen provides valuable information about these mysterious giants of the Antarctic deep. Sperm whales dive to depths of over 2,000 meters to hunt giant squid, holding their breath for up to 90 minutes during these deep dives. The sperm whale is the largest toothed predator on Earth, with adult males reaching lengths of 20 meters and weights of 50 tons. These massive animals are capable of remarkable diving feats. They regularly descend to depths of 1,000 meters or more, and the deepest recorded dive reached nearly 3,000 meters. At these depths, the pressure is immense, the temperature near freezing, and the darkness absolute. Yet sperm whales hunt there with apparent ease. They locate their prey, primarily giant and colossal squid, using echolocation, producing clicks that bounce off objects and return as echoes. The whales can interpret these echoes to create a sound picture of their surroundings, effectively seeing with sound in the darkness. When a whale finds a squid, it pursues and seizes the prey in its massive jaws. The battle between whale and squid often leaves marks. Many sperm whales bear circular scars on their skin, the marks of squid suckers, evidence of the struggles that occur in the deep ocean's darkness. The gulper eel has an enormous mouth that can open wide enough to swallow prey larger than itself, living at depths of up to 3,000 meters. This strange creature, also called the pelican eel, has a body built around its mouth. The jaw unhinges and expands to massive proportions, while the stomach stretches to accommodate large prey. The rest of the body is surprisingly small, tapering to a thin whip-like tail. The gulper eel can be up to a meter long, but most of that length is tail. The actual body and mouth section might only be 20 or 30 centimeters. When the eel encounters prey, it opens its enormous mouth like a net, engulfing whatever swims nearby. The prey is trapped in the expandable stomach, which swells to contain the meal. This ability to eat prey larger than oneself is crucial in the deep ocean where food is scarce and unpredictable. When a meal arrives, you must be able to take advantage regardless of its size. The gulper eel drifts slowly through the midnight zone, its mouth agape, waiting for something edible to swim into range. Vampire squid, despite their name, are harmless creatures that feed on marine snow, the constant rain of dead organic material drifting down from the surface. The vampire squid earned its dramatic name from its dark coloring and the skin that connects its 8 arms like a cape, reminiscent of vampire folklore. But this small squid, rarely exceeding 30 centimeters in length, is no predator. It feeds on detritus, using specialized filaments that extend from its body to collect particles of marine snow. These particles consist of dead plankton, fecal matter from animals living above, and other organic debris that continuously drifts downward through the ocean. The vampire squid extends its filaments into the water and allows particles to stick to them. Periodically, it reels in the filaments and passes them over its mouth, scraping off the collected material and consuming it. This feeding strategy is unique among cephalopods, most of which are active predators. The vampire squid's adaptation to eating marine snow allows it to survive in the nutrient-poor environment of the deep ocean, living at depths of 600 to 1,000 meters. The burrell fish has a transparent head that allows it to look upward through its skull to spot the silhouettes of prey against the faint light above. This remarkable fish possesses one of the strangest adaptations in the ocean. The top of its head is a transparent dome filled with clear fluid, and inside this dome sit two tubular eyes pointing upward. For years, scientists who examined dead specimens were puzzled by the barrel eye's anatomy, unable to understand how its visual system functioned. Only when researchers observed living burrell eyes in their natural habitat using submersibles did the mystery resolve. The fish can rotate its tubular eyes inside the transparent dome, allowing it to look upward to scan for prey or forward when pursuing it. The green lenses in its eyes filter out sunlight penetrating from above, instead optimizing vision for detecting the bioluminescence of its prey. The burrell eye typically hovers motionless in the water, its upward-gazing eyes searching for the silhouettes or bioluminescent flashes of small fish and jellyfish. When it spots prey, the eyes rotate forward and the fish pursues, using its remarkably adapted visual system to hunt in the twilight zone. Viperfish have teeth so long they cannot close their mouths completely, and they use bioluminescent organs to attract prey in the midnight zone. The viperfish's teeth are among the most fearsome in the ocean, proportionally the longest teeth of any fish. The fangs are so long that they do not fit inside the mouth when closed. Instead, they curve outward and upward, reaching nearly to the fish's eyes. To accommodate these enormous teeth, the viperfish has a hinged skull that can rotate upward, opening the mouth to enormous size when striking at prey. The first vertebra behind the skull acts as a shock absorber, allowing the head to snap forward with incredible force without damaging the spine. Along its belly, the viperfish has photophores that produce light, and one particularly large light organ sits at the end of a long dorsal fin ray that extends forward over the fish's head. This lure dangles in front of the viperfish, glowing softly in the darkness, attracting curious prey within striking distance. When prey approaches close enough, the viperfish strikes with lightning speed, impaling the prey on its fangs. The blobfish, which looks unremarkable in its natural deep-sea habitat, appears gelatinous because it is adapted to extreme pressure that keeps its body firm. The blobfish became famous, or perhaps infamous, as the world's ugliest fish based on photographs of specimens brought to the surface. In these images, the blobfish appears as a droopy, gelatinous mass with a face that seems permanently sad. But this appearance is misleading. At the depths where blobfish live, between 600 and 1,200 meters down, the pressure is 60 to 120 times greater than at the surface. In these conditions, the blobfish's body is firm and normal-looking. Its flesh, which is slightly less dense than water, allows it to hover just above the seafloor without expending energy to swim. When brought to the surface, however, the pressure drops dramatically, and without the external pressure to hold it together, the blobfish's body expands and sags, creating the droopy appearance that made it famous. In its natural habitat, the blobfish is simply a slow-moving predator that ambushes small invertebrates from its position hovering near the bottom. Fantooth fish have the largest teeth relative to body size of any fish in the ocean, living at depths where food is scarce and every meal counts. Despite their fearsome appearance, fantooth fish are relatively small, typically growing no longer than 15 centimeters. But their teeth are enormous, especially the two fangs in the lower jaw that are so long the fish has special sockets in its skull where the teeth fit when the mouth closes. If scaled up to human size, these teeth would be over 15 centimeters long. The fantooth lives in the midnight zone, between 500 and 5,000 meters deep, where prey is scarce and encounters with potential meals are rare. The enormous teeth ensures that when the fantooth does encounter prey, it can grip firmly and prevent escape. Young fantooth fish look completely different from adults, so different that scientists initially classified them as separate species. Juveniles are light gray, have smaller teeth, and possess long spines extending from their heads. They live in shallower water than adults, only descending to deeper zones as they mature and undergo their dramatic transformation. The Dumbo octopus, named for its ear-like fins, lives deeper than any other octopus species, at depths of up to 7,000 meters. These small octopuses, rarely exceeding 20 centimeters in length, have paired fins that protrude from the sides of their heads, like the ears of Disney's flying elephant. They flap these fins to propel themselves through the water in a swimming motion, quite unlike the jet propulsion used by most other cephalopods. Dumbo octopuses hover just above the ocean floor in the abyssal and hadal zones, occasionally descending to touch down on the soft sediment. They have large eyes relative to their body size, though vision is likely of limited use in the complete darkness of their habitat. Instead, they probably rely on touch and chemical sensing to find prey. Their diet consists primarily of small invertebrates that live in the sediment or just above it. The Dumbo octopus has a soft, gelatinous body, well suited to the extreme pressure of the deep ocean. Multiple species of Dumbo octopus exist, each slightly different in appearance, and new species continue to be discovered as exploration of the deepest ocean zones continues. Deep-sea dragonfish produce red bioluminescence, which most deep-sea creatures cannot see, giving them an invisible searchlight to find prey. Most deep-sea animals produce blue or green bioluminescence, and their eyes are sensitive only to these wavelengths. Red light is absorbed quickly by seawater and rarely occurs naturally at depth, so most deep-sea creatures lost the ability to see red wavelengths through evolution. The dragonfish exploited this blind spot. They evolved specialized light organs beneath their eyes that produce red light, along with retinas capable of detecting red wavelengths. This creates an enormous advantage. The dragonfish can illuminate its surroundings with red light, spotting prey clearly while remaining invisible to its targets. To the prey, the red beam is undetectable, leaving them unaware they have been spotted until the dragonfish strikes. Some species of dragonfish can also produce blue-green light from photophores along their bodies, perhaps for communication or to startle predators. The combination of visible and invisible light gives these predators multiple tools for survival in the deep ocean's darkness. The glass squid has a nearly transparent body, making it almost invisible in the deep ocean, with only its eyes giving away its presence. Transparency is an effective camouflage strategy in the open ocean where there is nowhere to hide. If predators cannot see you, they cannot chase you. The glass squid takes transparency to an extreme. Its tissues are so clear that you can see right through its body. Internal organs are visible as faint shadows, and light passes through the squid with minimal distortion. This transparency works best in the twilight zone, where some light still penetrates from above. In complete darkness, transparency offers no advantage, since there is no light to pass through the body anyway. The glass squid's main challenge is concealing its eyes. Eyes by their nature, must absorb light to function, so they cannot be transparent. The glass squid's eyes appear as dark spots on an otherwise invisible body. Some species have evolved reflective structures around the eyes to help mask them. Others position themselves with eyes pointing downward, making them less visible to predators hunting from below. Despite the challenge of concealing the eyes, transparency remains an effective defense for these delicate creatures. Tripod fish stand on the ocean floor, using elongated fins like stilts, waiting motionless for prey to drift within reach in the abyssal zone. These fish have 3 greatly elongated fin rays, 2 extending from the pelvic fins and 1 from the tail, that can be several times longer than the fish's body. The tripod fish positions these rays beneath itself, and stands perfectly still on the soft sediment of the abyssal plain, facing into the current. Food particles and small prey organisms drift past in the water, and the fish waits with its pectoral fins extended forward like nets. When something edible touches these fins, the fish snaps it up. This strategy requires minimal energy expenditure, important in an environment where food is scarce. The tripod fish can wait for hours or even days without moving, conserving every bit of energy until a meal arrives. Some tripod fish can reach lengths of 40 centimeters, including their fin extensions. They live at depths of 1,000 to 6,000 meters, making them among the deepest dwelling fish in the ocean. Their patient hunting strategy is perfectly suited to life on the abyssal plains, where the current brings an occasional but unpredictable supply of food. The frilled shark, sometimes called a living fossil, has remained largely unchanged for 80 million years, and lives at depths of 600 to 1,000 meters. This primitive-looking shark has features that more closely resemble ancient shark ancestors than modern species. Its body is eel-like, long and flexible, quite different from the streamlined torpedo shape of most modern sharks. Its mouth is positioned at the front of its head rather than underneath, and when opened, it reveals 25 rows of backward-pointing teeth, each with 3 sharp prongs. These teeth interlock when the mouth closes, forming a trap from which prey cannot escape. The frilled shark feeds primarily on squid, using its flexible body to lunge forward and engulf prey in one swift motion. Its gill slits, 6 pairs, instead of the 5 pairs found in most sharks, are frilled and ruffled, giving the shark its name. The frilled shark grows slowly and reproduces slowly, with pregnancies lasting up to 3.5 years, the longest gestation period of any vertebrate. This slow reproduction makes the species vulnerable to overfishing, though it has survived in the deep ocean for millions of years, relatively unchanged. Coral reefs, though they cover less than 1% of the ocean floor, support about 25% of all marine species. This extraordinary concentration of biodiversity makes coral reefs among the most productive ecosystems on Earth, rivaling tropical rainforests in the sheer variety of life they support. Thousands of fish species make their homes among the coral structures. Invertebrates of every description, from tiny shrimp to large octopuses, find shelter in the reef's countless crevices. Sea turtles feed on seagrass beds near reefs, and rest in reef caves at night. Sharks patrol the deeper waters around reef edges. The three-dimensional structure of the reef creates countless microhabitats, each supporting its own community of specialized organisms. Some creatures live only on the tops of coral formations, where light is strongest. Others inhabit the shaded undersides. Still others burrow into the coral rock itself. Thousands of fish species make their homes among the coral structures. Invertebrates of every description, from tiny shrimp to large octopuses, find shelter in the reef's countless crevices. Sea turtles feed on seagrass beds near reefs, and rest in reef caves at night. sharks patrol the deeper waters around reef edges. The Great Barrier Reef, visible from space, stretches over 2,300 kilometers, and is the largest living structure on Earth. Located off the coast of northeastern Australia, the Great Barrier Reef is not a single reef, but a vast system of nearly 3,000 individual reefs and 900 islands stretching along the Queensland coast. From above, the reef appears as a patchwork of blue and turquoise waters, with lighter areas marking shallow reefs and darker blue indicating deeper channels between them. Astronauts in orbit have photographed the reef, and satellites regularly capture images of this massive structure. The reef began forming around 20 million years ago, though the current structure is much younger, developing over the past 8,000 years, since sea levels stabilized after the last ice age. The Great Barrier Reef covers an area of approximately 344,000 square kilometers, larger than the United Kingdom. It supports an estimated 1,500 species of fish, 400 species of coral, 4,000 species of mollusks, and countless other organisms, making it one of the most biodiverse places on Earth. Coral polyps are tiny animals that build massive reef structures from calcium carbonate secreted from their bodies over thousands of years. Each individual coral polyp is a small, soft-bodied animal related to jellyfish and sea anemones. A polyp might measure only a few millimeters across, with a cylindrical body topped by a ring of tentacles surrounding a central mouth. Despite their small size, these animals are master builders. They extract calcium and carbonate ions from seawater, and combine them to form calcium carbonate, the same material that makes up limestone. The polyp deposits this calcium carbonate at its base, creating a hard cup-shaped skeleton in which it lives. As the polyp grows and reproduces, it builds upward and outward, and the calcium carbonate skeleton grows with it. A single polyp might create only a tiny amount of skeleton during its lifetime, but a coral colony contains thousands or millions of polyps, all building simultaneously. Over centuries and millennia, these countless tiny contributions accumulate into the massive structures we recognize as coral reefs. Some reefs have been growing continuously for thousands of years, layer upon layer of calcium carbonate deposited by countless generations of polyps. Many coral species have symbiotic relationships with algae, called zooxanthellae, which live inside coral tissue and provide food through photosynthesis. These microscopic algae live within the cells of the coral polyp's tissue, giving healthy coral its characteristic brown, green, or golden coloration. Over centuries and millennia, these countless tiny contributions accumulate into the massive structures we recognize as coral reefs. Some reefs have been growing continuously for thousands of years, layer upon layer of calcium carbonate deposited by countless generations of polyps. This relationship allows corals to thrive in the nutrient-poor tropical waters, where reefs typically form. Without zooxanthellae, most reef-building corals could not grow fast enough to create the massive structures we see today. The partnership is so crucial that coral and zooxanthellae often cannot survive without each other. Young coral larvae acquire their zooxanthellae from the environment, and the algae must colonize the coral tissue for the polyp to survive long-term. This intimate partnership between animal and plant has enabled the construction of the ocean's most magnificent structures. When ocean temperatures rise, corals expel their zooxanthellae in a process called bleaching, which can lead to coral death if conditions don't improve. The symbiotic relationship between coral and zooxanthellae is sensitive to environmental conditions, particularly temperature. When water temperatures rise, even a few degrees above normal for an extended period, the zooxanthellae begin producing toxic compounds in response to the stress. The coral polyp, detecting these toxins, expels the algae from its tissues in a desperate attempt to protect itself. Without the zooxanthellae, the coral loses its color, appearing white or bleached as the translucent tissue reveals the white calcium carbonate skeleton beneath. The coral is not yet dead at this stage, but it is severely weakened. It has lost its primary food source, and must rely entirely on capturing prey with its tentacles, a far less efficient method of obtaining nutrition. If water temperatures return to normal within a few weeks, the coral can acquire new zooxanthellae and recover. But if elevated temperatures persist for months, the starving coral dies. Mass bleaching events have become increasingly common in recent decades, causing widespread coral mortality and transforming once vibrant reefs into graveyards of white skeletons. Kelp forests grow in cold, nutrient-rich waters and can reach heights of 45 meters, creating underwater forests teeming with life. Kelp are large brown algae that grow in dense stands along temperate coastlines, particularly in the cold waters of the Pacific coast of North America, southern Australia, and the coast of South America. Individual kelp plants anchor to rocky substrate on the seafloor using a structure called a holdfast, then grow upward toward the surface at remarkable speeds. Giant kelp, the largest species, can grow up to 60 centimeters per day under ideal conditions, making it one of the fastest growing organisms on Earth. The kelp steep, analogous to a stem, rises from the holdfast, and blade-like fronds branch off at intervals, each with a gas-filled bladder that provides buoyancy. The blades form a dense canopy near the water's surface where sunlight is strongest. This three-dimensional structure creates multiple layers of habitat. Fish hide among the holdfasts near the bottom. Sea urchins graze on kelp tissue. Seals hunt in the kelp canopy. Sea otters wrap themselves in kelp fronds to prevent drifting while they sleep. Sea otters play a crucial role in kelp forest ecosystems by eating sea urchins, which would otherwise overgraze and destroy the kelp. This relationship illustrates the concept of a keystone species, an organism whose presence has a disproportionately large effect on its ecosystem relative to its abundance. Sea otters feed extensively on sea urchins, consuming large numbers each day to support their high metabolic rate. Sea urchins, in turn, feed on kelp. When sea otters are present in an ecosystem, they keep urchin populations in check, preventing the urchins from overgrazing the kelp. The kelp forest remains healthy and diverse, supporting a wide variety of species. When sea otters are removed from the ecosystem, either through hunting or disease, urchin populations explode. Without predators to control them, the urchins consume kelp faster than it can grow. The kelp forest transforms into an urchin barren, a rocky wasteland covered with sea urchins and little else. The loss of the kelp forest cascades through the ecosystem, eliminating habitat for fish, invertebrates, and other species that depended on the kelp. This dramatic transformation demonstrates the critical importance of predators in maintaining ecosystem balance. The Sargasso Sea, located in the North Atlantic, has no land boundaries and is defined by ocean currents that create a vast floating forest of seaweed. Unlike other seas that are bordered by continents, the Sargasso Sea is bounded by currents. The Gulf Stream marks its western and northern boundaries. The North Atlantic Current its northern edge, and the Canary Current its eastern boundary. These currents circulate in a clockwise pattern, creating a relatively calm area of ocean in their center. This calm region accumulates floating sargassum seaweed, a brown algae that reproduces vegetatively, creating new plants from fragments that break off. The seaweed forms dense mats that cover vast areas of the surface, creating a unique open ocean habitat. The Sargasso Sea covers approximately 5 million square kilometers in the western North Atlantic, making it one of the largest ecosystems on Earth. The water is exceptionally clear and blue, earning the region the nickname the Crystal Sea. Despite being far from any coast, the Sargasso Sea supports a remarkable diversity of life, all adapted to living in or around the floating seaweed. This seaweed provides habitat for countless species, including young sea turtles, that drift there during their early years. The floating sargassum creates an oasis of life in the open ocean. Small fish hide among the fronds, protected from predators. Shrimp and crabs cling to the seaweed, camouflaged by their brown coloration. Juvenile turtles, after hatching on distant beaches, make their way to the Sargasso Sea, where they spend their first years of life. The seaweed provides them with shelter from predators, and a rich supply of food. Small fish, invertebrates, and other prey thrive in the sargassum, giving the young turtles ample opportunity to feed and grow. Some species exist only in the Sargasso Sea, having evolved specifically to exploit this unique habitat. The sargassum fish, for instance, has elaborate fins and coloration that perfectly mimic the seaweed, allowing it to ambush prey while remaining nearly invisible. Flying fish attach their eggs to the seaweed using adhesive threads. Eels from both sides of the Atlantic migrate to the Sargasso Sea to spawn. Despite being in the middle of the ocean, far from any coast, the Sargasso Sea functions as a critical nursery and breeding ground. Mangrove forests grow along tropical coastlines, their roots providing crucial nursery habitat for many fish species, and protecting shorelines from erosion. Mangroves are trees adapted to grow in saltwater, a challenging environment that most plants cannot tolerate. They have evolved specialized root systems that extend above the water's surface, allowing the trees to breathe even when submerged at high tide. These prop roots create a complex three-dimensional structure, both above and below the water. The underwater portions of the roots provide attachment surfaces for oysters, barnacles, and sponges. Small fish hide among the roots, protected from larger predators that cannot navigate the dense tangle. Many commercially important fish species, including snappers, groupers, and tarpon, spend their juvenile stages in mangrove forests before moving to coral reefs or open ocean as adults. The mangrove roots also protect coastlines from erosion by dissipating wave energy and trapping sediment. During storms and tsunamis, mangrove forests act as natural buffers, reducing the impact of waves on coastal communities. Despite their importance, mangrove forests worldwide have declined dramatically due to coastal development, particularly for shrimp farming and agriculture. Seagrass meadows, found in shallow coastal waters, produce more oxygen per area than rainforests, and provide food for manatees, dugongs, and sea turtles. These underwater flowering plants form extensive meadows in shallow waters, where sunlight can penetrate to the seafloor. Unlike seaweeds, which are algae, seagrasses are true plants with roots, stems, and leaves. They photosynthesize extremely efficiently, producing oxygen at rates that exceed those of terrestrial forests when compared area for area. A healthy seagrass meadow can produce 10 liters of oxygen per square meter per day. The plants also sequester carbon in their tissues and in the sediment beneath them, helping to mitigate climate change. Seagrass meadows provide critical habitat for a wide variety of species. Small fish and invertebrates live among the grass blades. Larger fish visit to hunt the smaller species. Sea turtles graze on seagrass leaves. Manatees and dugongs, the only herbivorous marine mammals, feed almost exclusively on seagrass, consuming up to 15% of their body weight daily. The meadows also stabilize sediments, reducing erosion and maintaining water clarity. Despite their importance, seagrass meadows face threats from coastal development, pollution, and boat propellers. The Arctic Ocean, covered in ice for much of the year, supports unique ecosystems including ice algae that grow on the underside of sea ice. At first glance, Arctic sea ice appears lifeless, a frozen wasteland devoid of vegetation. But the underside of the ice tells a different story. Ice algae, microscopic plants specially adapted to cold conditions, colonize the bottom surface of sea ice where it meets the water. These algae can photosynthesize using the limited light that penetrates through the ice from above. As daylight returns to the Arctic after the winter darkness, the algae begin to grow, forming greenish-brown layers on the ice's underside. These algae are incredibly productive, creating dense blooms that provide food for zooplankton, particularly copepods and krill. These small crustaceans in turn feed fish, seals, and whales. The ice algae bloom occurs earlier in the year than the phytoplankton bloom in the open water, providing crucial early-season food for Arctic marine life. As climate change reduces the extent and thickness of Arctic sea ice, the ice algae habitat shrinks, potentially disrupting the Arctic food web. Polar bears, though they live on land and ice, are considered marine mammals because they depend almost entirely on the ocean for food. The polar bear's scientific name, Ursus maritimus, means maritime bear, reflecting its dependence on the marine environment. Though polar bears mate, den, and rest on land or ice, they hunt in the ocean environment, primarily targeting seals. Ringed seals and bearded seals make up the bulk of their diet. Polar bears hunt seals by waiting beside breathing holes in the ice, pouncing when a seal surfaces to breathe. They also stalk seals resting on the ice, using their white fur as camouflage against the snow. In summer, when sea ice retreats from the coast, polar bears sometimes fast for months, living off fat reserves built up during the winter hunting season. Climate change is reducing the extent and duration of sea ice, forcing polar bears to spend more time on land and less time hunting. This leads to longer fasting periods and declining body condition. Some bears have learned to hunt reindeer or raid bird colonies for eggs, but these terrestrial prey cannot fully replace the energy-rich seal blubber that polar bears need. Antarctic waters, despite being frozen for much of the year, are incredibly productive due to seasonal upwellings of nutrient-rich water. The Southern Ocean surrounding Antarctica is one of the most productive marine ecosystems on Earth. During winter, the ocean surface freezes, creating sea ice that extends far from the continent. As spring arrives, the ice begins to melt, and several factors combine to create ideal conditions for phytoplankton growth. The melting ice releases fresh water that floats on top of the denser salt water, creating a stable surface layer. The increasing daylight provides energy for photosynthesis. Most importantly, upwelling currents bring nutrient-rich deep water to the surface. These nutrients, accumulated in the deep ocean over months or years, fertilize the surface waters. Phytoplankton bloom in massive numbers, turning the water green. This abundance of microscopic plants supports enormous swarms of krill, small shrimp-like crustaceans that form the foundation of the Antarctic food web. Everything from fish to penguins to whales feeds on krill. A single swarm of Antarctic krill can contain millions of tons of biomass, making them among the most abundant animals on Earth. Krill, small shrimp-like creatures in Antarctic waters, form swarms so massive they can be seen from space and form the base of the Southern Ocean food web. Antarctic krill, scientifically named Euphausia superba, grow to about 6 centimeters in length and weigh only a couple of grams. But what they lack in individual size, they make up for in numbers. Scientists estimate the total biomass of Antarctic krill at between 300 and 500 million tons, making them potentially the most abundant animal species on Earth by weight. They gather in enormous swarms that can stretch 4 kilometers, and contain krill densities so high the water appears pink or red. These swarms show up on sonar and can be detected from satellites. Krill feed on phytoplankton and ice algae, filtering tiny plants from the water with their feathery legs. They in turn become food for nearly every predator in Antarctic waters. Penguins dive to catch krill. Seals hunt krill swarms. Blue whales, the largest animals ever to exist, migrate to Antarctic waters specifically to feed on krill, consuming several tons per day during the summer feeding season. The entire Antarctic ecosystem depends on these small crustaceans. The blue whale is the largest animal ever known to have lived on Earth, reaching lengths of 30 meters and weights of up to 200 tons. To comprehend the size of a blue whale, consider that its tongue alone weighs as much as an elephant. Its heart is the size of a small car, weighing around 400 kilograms. A human could crawl through its largest blood vessels. When a blue whale exhales, its breath can shoot up to 9 meters into the air, creating a distinctive blow that allows observers to identify the species from a distance. Despite being the largest animal to ever exist, larger than any dinosaur, blue whales feed on some of the smallest creatures in the ocean. They are baleen whales, meaning they lack teeth and instead have plates of baleen hanging from their upper jaws. These plates act as filters, allowing water to pass through while trapping food. Blue whales feed primarily on krill, gulping enormous mouthfuls of water and krill, then forcing the water out through the baleen while retaining the krill. A blue whale must consume around 4 tons of krill per day during the feeding season to maintain its massive body. Despite their enormous size, blue whales feed almost exclusively on tiny krill, filtering tons of water through baleen plates in their mouths. The blue whale's feeding strategy seems paradoxical. Why would the largest animal on Earth eat some of the smallest? The answer lies in efficiency and abundance. Krill swarms can contain millions of individuals, concentrated in relatively small areas. By targeting these dense aggregations, blue whales can consume vast quantities of food with each lunge. The whale approaches a krill swarm, opens its mouth to nearly 90 degrees, and accelerates forward, engulfing up to 100 tons of water and krill in a single gulp. Pleated grooves along its throat expand like an accordion, allowing the mouth to balloon to several times its normal size. Once the mouth is full, the whale closes it and uses its massive tongue to force the water out through the baleen plates. The baleen, made of keratin-like fingernails, has a frayed inner edge that acts as a sieve. Water escapes, but krill remain trapped. The whale swallows the trapped krill and repeats the process. This feeding method is called lunge feeding, and it allows blue whales to consume the enormous quantities of food needed to fuel their massive bodies. Whale songs can travel thousands of kilometers through the ocean, with some low-frequency calls possibly traveling across entire ocean basins. Sound travels much farther and faster in water than in air, a property that whales exploit for long-distance communication. Whale songs, particularly those of humpback and blue whales, contain extremely low-frequency components, some below the range of human hearing. These low-frequency sounds travel vast distances through the ocean, with minimal energy loss, especially in a layer of water called the surf channel, which acts as an acoustic waveguide. The SOFAR channel exists at depths of around 1,000 meters, where temperature and pressure create conditions that minimize sound absorption. Sounds produced in this channel can travel for thousands of kilometers before dissipating. Blue whales produce some of the loudest sounds in the animal kingdom. reaching volumes of up to 188 decibels. A whale off the coast of California might produce a call that reaches whales near Japan. This long-distance communication might help widely dispersed whales coordinate their movements, locate feeding areas, or find mates across vast stretches of ocean. Humpback whales create complex songs that can last up to 20 minutes and are repeated for hours, with all males in a region singing similar songs. Humpback whale song is among the most complex vocalizations in the animal kingdom. Each song consists of multiple themes, and each theme contains several phrases made up of individual units of sound. A complete song might last 15 to 20 minutes, and individual whales sing the same song repeatedly for hours or even days. The songs are produced exclusively by males, particularly during the breeding season, suggesting they play a role in courtship or competition. What makes humpback songs truly remarkable is their cultural transmission. All males in a particular ocean region sing very similar versions of the song in any given year, suggesting they learn from each other. The songs evolve over time, with new phrases introduced, and old ones modified or dropped. By the next breeding season, the song has changed, sometimes dramatically. Yet all males in the region still sing roughly the same version. This pattern of shared cultural evolution is rare in the animal kingdom, found otherwise mainly in humans and some songbirds. These songs change gradually over time, with new phrases introduced and old ones dropping out, similar to the evolution of human language and music. Researchers who have studied humpback whale songs over decades have documented how certain phrases become popular and spread through the population, while others fade away and disappear. The mechanism appears to be social learning, where whales listen to each other and adjust their songs to match the current trend. Some changes are subtle, like a slight alteration in the pitch or duration of a phrase. Other changes are more dramatic, with entirely new sequences appearing seemingly out of nowhere. In the western South Pacific, researchers documented an extraordinary event where a completely new song swept through the entire population of humpback whales. The song originated near Australia and spread eastward across thousands of kilometers, reaching French Polynesia within just 2 years. By the time the song reached the eastern edge of the population's range, it had replaced the previous song entirely. This rapid cultural transmission suggests that humpback whales are highly attuned to the songs of others and capable of learning and reproducing complex acoustic patterns with remarkable fidelity. Dolphins use echolocation to navigate and hunt, emitting clicks that bounce off objects and return, creating a sound picture of their surroundings. Echolocation allows dolphins to perceive their environment in complete darkness or murky water where vision is useless. A dolphin produces clicking sounds in air sacs near its blowhole, and these sounds are focused into a beam by an organ in its forehead called the melon. The clicks travel through the water and bounce off objects in the dolphin's path. The returning echoes are received through the dolphin's lower jaw, which contains specialized fat deposits that conduct sound to the inner ear. The dolphin's brain processes these echoes, extracting information about the distance, size, shape, and even internal structure of objects. Dolphins can detect a fish buried in sand, or a small object over 100 meters away. The resolution of dolphin echolocation is remarkable. Experiments have shown dolphins can distinguish between objects that differ by less than a millimeter in size. They can identify different species of fish, based solely on the echoes. This biological sonar is so sophisticated that navies have studied dolphin echolocation to improve human-made sonar systems. Some dolphin species have been observed using tools, such as carrying sponges on their rostrums to protect them while foraging on the ocean floor. In Shark Bay, Australia, researchers documented a fascinating example of tool use in bottlenose dolphins. Certain individuals, almost exclusively females, tear off pieces of basket sponge from the seafloor and wear them over their rostrums like protective gloves. They then use these sponge tools while foraging on the sandy bottom, probing and digging for fish hiding in the substrate. The sponge protects the dolphin's rostrum from sharp rocks, coral fragments, and venomous creatures that might be buried in the sand. This behavior is not instinctive but learned, passed from mother to daughter through observation and imitation. Researchers call this vertical cultural transmission. Daughters of spun-using mothers are far more likely to adopt the behavior than daughters of non-users. This represents a form of cultural evolution, where a beneficial innovation is maintained and transmitted through social learning rather than genetic inheritance. Tool use was once considered unique to humans and a few primate species. But observations like these demonstrate that dolphins possess the cognitive flexibility to innovate solutions, and the social structures to transmit innovations culturally. Orcas, or killer whales, are actually the largest members of the dolphin family, and live in tight-knit family groups with unique hunting strategies and dialects. Despite their common name, orcas are not whales but dolphins. Closely related to bottlenose dolphins and other dolphin species. Adult males can reach 9 meters in length and weigh up to 6 tons, making them formidable predators. Orcas live in matriarchal family groups called pods, typically consisting of an older female, her daughters, and her daughters' offspring. Males generally remain with their birth pod for life. Each pod develops its own culture, including unique vocalizations called dialects. Pods that share dialects form acoustic clans, suggesting they share common ancestry. Different orca populations have evolved specialized hunting strategies suited to their local prey. Resident orcas in the Pacific Northwest feed primarily on salmon, using sonar to locate fish and coordinating their movements to herd salmon into tight groups. Transient orcas hunt marine mammals, employing stealth and silence to avoid alerting their prey. Antarctic orcas use wave-washing techniques to knock seals off ice floes. These hunting strategies are learned and transmitted culturally, with young orcas spending years learning their pods techniques. Different orca populations have distinct cultures, with some specializing in hunting fish, others hunting marine mammals, and some preferring sharks. The cultural differences between orca populations are so profound that some researchers believe they may represent different species or subspecies. Resident orcas that feed on fish have different teeth wear patterns than transient orcas that hunt mammals, as fish require less force to tear apart than seal or sea lion flesh. Their hunting techniques differ dramatically. Fish-eating orcas are vocal, using echolocation constantly to locate salmon. Mammal-hunting orcas remain silent for most of their hunt, as marine mammals can hear orca vocalizations and flee. Off the coast of New Zealand, some orca populations specialize in hunting rays. In the Gulf of California, orcas hunt whale sharks, the largest fish in the ocean. Some populations in the Southern Ocean have learned to depredate fishing vessels, stealing fish directly from land. These cultural traditions can be remarkably specific. One population off Argentina beaches itself, temporarily to snatch seal pups from the shore, a dangerous technique that requires precise timing and experience. Mothers teach this technique to their calves in shallow practice sessions before attempting it in earnest. Elephant seals can dive to depths of over 2,000 meters, and hold their breath for up to 2 hours, while hunting for squid and fish. These impressive marine mammals are champion divers, surpassing most whale species in diving ability. northern elephant seals, found along the Pacific coast of North America, and southern elephant seals, found in Antarctic and subantarctic waters, spend most of their lives at sea, coming ashore only to breed and molt. During their months at sea, they dive almost continuously, spending only a few minutes at the surface between dives. A typical dive lasts 20 to 30 minutes, and reaches depths of 400 to 600 meters. But elephant seals are capable of far deeper and longer dives. The deepest recorded dive exceeded 2,300 meters, and the longest recorded dive lasted nearly 2 hours. During these prolonged dives, the seals hunt for squid and fish in the deep ocean. To survive these extreme dives, elephant seals have numerous adaptations. Their blood contains high concentrations of hemoglobin and myoglobin to store oxygen. They can slow their heart rate dramatically, from about 100 beats per minute at the surface, to as low as 4 beats per minute during deep dives. Manatees and dugongs, collectively called sea cows, are the only herbivorous marine mammals, grazing on seagrass in shallow tropical waters. These gentle giants evolved from land mammals that returned to the sea around 50 million years ago. Unlike seals and whales, which are carnivores, sea cows feed exclusively on plants. Manatees, found in the Caribbean and along the southeastern coast of the United States, can weigh up to 600 kilograms. Dugongs, found in the Indo-Pacific region, are slightly smaller and have a fluked tail similar to whales, while manatees have a rounded paddle-like tail. Both species spend their days grazing on seagrass meadows, using their flexible lips to grasp and tear vegetation. A manatee can consume up to 15% of its body weight in vegetation daily, sometimes eating over 40 kilograms of seagrass in a 24-hour period. This constant grazing plays an important ecological role, as it promotes seagrass growth by removing old blades and stimulating new growth. Sea cows have low metabolic rates and move slowly. Adaptations to a diet of nutrient-poor seagrass. They inhabit warm, shallow waters where seagrass grows, making them vulnerable to boat strikes. One of the leading causes of manatee deaths in populated coastal areas. Narwhals, sometimes called the unicorns of the sea, possess a long spiral tusk that is actually an elongated tooth extending from their upper jaw. The narwhal's tusk, which can grow up to 3 meters long and weigh up to 10 kilograms, is one of nature's most unusual adaptations. The tusk develops from the left canine tooth in males, growing forward through the upper lip in a spiral pattern with a left-handed helix. About 1 in 500 males develops 2 tusks, with both canine teeth elongating. Females rarely develop tusks. For centuries, the function of this extraordinary tooth puzzled scientists. Early theories suggested it was used as a weapon for fighting or for breaking ice. But observations of narwhals rarely show aggressive tusk use, and the tusk is too fragile for breaking ice. Recent research revealed that the tusk is a sensory organ. The outer surface contains millions of tiny pores connecting to nerve pathways, making it incredibly sensitive to temperature, pressure, and chemical changes in the water. Narwhals might use their tusks to detect changes in water salinity, helping them navigate through Arctic waters, or to sense the presence of prey fish. These tusks can grow up to 3 meters long, and are filled with millions of nerve endings, possibly used to sense changes in water temperature and salinity. The discovery that narwhal tusks function as sensory organs revolutionized understanding of these Arctic whales. The tusk's structure is remarkable. Unlike ordinary teeth with nerves only in the interior, the narwhal tusk has channels running from the nerve-rich pulp cavity through the dentin to the outer surface. This creates a direct connection between environmental conditions and the whale's nervous system. Narwhals have been observed rubbing their tusks together, an activity called tusking, which might allow them to share sensory information. The sensitivity of the tusk is extraordinary. In laboratory experiments with extracted tusks, researchers found they could detect temperature changes of mere fractions of a degree in salinity, variations of less than 1 part per thousand. This sensitivity might help narwhals navigate in the ice-covered Arctic waters where they live, detecting freshwater currents from glacial melt, or changes in salinity that indicate open water. The tusk might also play a role in finding prey, detecting the minute electrical fields generated by fish, or assessing the quality of potential mates. Sea lions and seals, though similar in appearance, belong to different families, with sea lions having external ear flaps and the ability to rotate their hind flippers forward. These two groups of marine mammals, though superficially similar, have different evolutionary histories and adaptations. Sea lions, along with fur seals, belong to the family Otaridae, known as eared seals, because of their external ear flaps. True seals, belonging to the family Phaceida, have no external ear structure, only ear openings. The difference in limb structure is even more significant. Sea lions can rotate their hind flippers forward, allowing them to walk on all fours on land with a distinctive lumbering gait. True seals cannot rotate their hind flippers, and must drag themselves across land using their front flippers, moving in an awkward caterpillar-like motion. In water, however, true seals are often more agile, using their hind flippers for propulsion, while sea lions rely more on their front flippers. Sea lions tend to be more social and vocal than true seals, gathering in large colonies and communicating with barks and roars. True seals are generally quieter and less gregarious, though there are exceptions in both groups. Walruses use their sensitive whiskers to detect clams and other prey on the dark ocean floor, and their tusks to help haul themselves onto ice. The Pacific walrus can weigh up to 2,000 kilograms, making it one of the largest pinnipedes. Both males and females possess tusks, which are elongated upper canine teeth that can grow to over a meter in length. While tusks play a role in social dominance displays and fighting, particularly among males competing for mates, they also serve a practical function. Walruses use their tusks as ice picks, hooking them over the edge of ice floes to help haul their massive bodies out of the water. This behavior gives walruses their family name, Odobenidae, derived from a Scandinavian word meaning toothed walker, for finding food. However, walruses rely on their whiskers. They possess about 400 stiff whiskers, called vibrissae, around their mouths. These whiskers are incredibly sensitive to touch and vibration. When feeding, a walrus dives to the seafloor and sweeps its snout across the sediment, using its whiskers to detect buried clams, mussels, and other invertebrates. When prey is detected, the walrus uses its muscular lips to create a powerful suction, extracting the soft parts and leaving the shells behind. A single walrus can consume thousands of clams in one feeding session. Whale falls, the carcasses of dead whales sinking to the ocean floor, create temporary ecosystems that can support unique communities for decades. When a whale dies and its body sinks to the deep ocean floor, it becomes an oasis of food in an environment where nutrition is scarce. A single whale carcass can provide more organic matter than the seafloor in that area receives in an entire year from the slow rain of marine snow. The whale fall progresses through several distinct stages, each supporting different communities of organisms. In the first stage, mobile scavengers arrive within hours or days. Hagfish, sleeper sharks, and deep-sea fish tear into the soft tissues. consuming the whale's flesh in a feeding frenzy that can last months or even years, depending on the whale's size. As the soft tissue disappears, the second stage begins. Opportunistic colonizers move in, including polychaete worms, crustaceans, and mollusks that feed on the remaining scraps of tissue and the lipid-rich bones. This stage can last 1 to 2 years. The third stage, called the sulfophilic stage, can last for decades. Bacteria colonize the bones, breaking down the lipids within and producing hydrogen sulfide, creating conditions similar to hydrothermal vent ecosystems. Over 400 species have been found living on or around whale falls, many of which exist nowhere else on Earth. The diversity of life supported by whale falls is extraordinary and includes numerous species that have never been found in any other habitat. These species are called whale fall specialists, organisms that have evolved to exploit the unique conditions created by decomposing whale carcasses. Giant bone-eating worms called osedacs, discovered only in the early 2000s, burrow into whale bones to access the lipids inside. These worms have no mouth or digestive system. Instead, they rely on symbiotic bacteria living in their tissues to digest the bone lipids for them. The females look like tiny red feathers growing from the bone, while males are microscopic and live inside the female's tubes. Other whale fall specialists include certain species of mussels, clams, and snails that also harbor sulfur-oxidizing bacteria. Scientists believe whale falls may serve as stepping stones, allowing deep-sea species to disperse across the ocean floor by moving from one carcass to another over evolutionary time. The vertical migration, where billions of small fish and invertebrates rise toward the surface at night and descend during the day, is the largest migration on Earth. Every night, as the sun sets and darkness falls over the ocean, countless creatures begin to swim upward from the deep. This phenomenon, called diel vertical migration, involves more animals than any other migration on the planet. Lanternfish, squid, jellyfish, krill, and countless other species ascend from depths of several hundred meters to feed in the productive surface waters under cover of darkness. The scale is staggering. In some regions, acoustic surveys show that up to 40% of all fish biomass participates in this nightly journey. The migration occurs in nearly all ocean regions, from the tropics to the poles. As dawn approaches, the animals descend back into the deep, returning to darker waters before the sun rises. This daily rhythm has continued for millions of years, driven by a simple survival strategy. Surface waters contain abundant food in the form of phytoplankton and the zooplankton that feed on them. But they also expose small creatures to predators that hunt by sight. By feeding at night and hiding in the dark depths during the day, these organisms minimize their risk of being eaten. This daily migration allows deep-sea creatures to feed in nutrient-rich surface waters under cover of darkness, then return to the safety of the depths at dawn. The vertical migration represents a carefully balanced trade-off between the benefits of accessing food and the risks of predation. The migration also plays a crucial role in ocean nutrient cycling. Organisms feed at the surface during the night, consuming phytoplankton and zooplankton. They then descend to deep waters during the day, where they digest their food and excrete waste. This process, called the biological pump, transports carbon and nutrients from the surface to the deep ocean. When the migrating organisms are eaten by deep-dwelling predators, or when they eventually die, the carbon in their bodies sinks to the ocean floor rather than returning to the atmosphere. Scientists estimate that diel vertical migration transports billions of tons of carbon to the deep ocean each year, making it a significant factor in Earth's carbon cycle. Certain shark species must keep swimming to breathe, as water must constantly flow over their gills, meaning they never fully rest. These sharks, called obligate ram ventilators, include many of the ocean's most iconic predators such as great white sharks, mako sharks, and whale sharks. Unlike most fish, which can pump water over their gills while stationary, these sharks must swim continuously to force water through their mouths and over their gill tissues where oxygen is extracted. If they stop swimming, they suffocate. This requirement shapes every aspect of their lives. They cannot rest on the seafloor like many other shark species. Instead, they must keep moving constantly, day and night, for their entire lives. How then do they sleep? Research suggests they may engage in unihemispheric sleep, where one half of the brain rests while the other half remains alert and controls swimming. This same strategy is used by dolphins and some seabirds. Alternatively, these sharks might sleep very lightly while continuing to swim, with reduced brain activity, but not complete unconsciousness. The constant swimming requires significant energy, which these sharks must obtain through frequent feeding on energy-rich prey like seals, tuna, and other large fish. Other sharks can pump water over their gills, while resting on the ocean floor, allowing them to sleep in caves and crevices. Most shark species are buccal pumpers, meaning they can actively pump water into their mouths and over their gills, using muscles in their cheeks and throat. This ability allows them to remain stationary while still breathing effectively. Nurse sharks, for example, spend much of the day resting in caves or under ledges, pumping water over their gills while they doze. Wobbegong sharks lie camouflaged on the seafloor, breathing steadily while waiting for prey to approach. Port Jackson sharks wedge themselves into rocky crevices, sometimes stacking on top of each other in favored resting spots. These sharks hunt primarily at night, emerging from their daytime refuges as darkness falls to search for food. Their ability to rest during the day provides an energy conservation advantage, while obligate ram ventilators must swim constantly and therefore feed more frequently. Buccal pumping sharks can reduce their activity levels during periods when prey is scarce. Some species switch between swimming and resting depending on conditions. In areas with strong currents, they might orient themselves to face the flow, allowing the current to push water over their gills without effort. Manta rays gather in specific locations called cleaning stations, where smaller fish remove parasites and dead skin from their bodies. These cleaning stations function like underwater car washes, attracting manta rays from wide areas. The stations are typically located on coral reefs or rocky outcrops where cleaner fish establish territories. Cleaner wrasses, small, brightly colored fish, perform most of the cleaning. They swim over the manta's body surface, into its mouth, and even inside its gill slits, picking off parasites, dead skin, and infected tissue. The manta remains nearly motionless during cleaning, sometimes hovering in the water with its mouth open to allow the cleaners access. Occasionally, a manta performs a slow barrel roll, presenting different parts of its body to the cleaners. These cleaning sessions can last several minutes, with multiple cleaner fish working simultaneously on a single manta. The relationship benefits both parties. The manta gets rid of parasites and maintains healthy skin. The cleaner fish get an easy meal. Researchers have documented individual mantas returning to the same cleaning stations repeatedly over months and years, suggesting they remember the locations and value the service provided. Some cleaning stations attract dozens of mantas, creating remarkable opportunities for divers to observe these graceful giants. These cleaning stations serve as social hubs, where rays can be seen repeatedly visiting the same locations over many years. The social aspect of cleaning stations extends beyond the simple exchange of cleaning services for food. Manta rays appear to use these locations as meeting places. Individual rays, which are solitary for most of their lives, encounter other mantas at cleaning stations. Researchers studying photo-identified individuals have found that certain rays show up at specific stations with remarkable regularity, visiting the same sites week after week, year after year. Some cleaning stations attract predominantly female rays, while others seem to be preferred by males. During mating season, cleaning stations can become courtship areas, where males pursue females. The consistent use of these locations has allowed researchers to conduct long-term studies of manta ray populations, photographing unique spot patterns on each individual's ventral surface to create identification catalogs. These studies revealed that manta rays have complex social structures and individual personalities. Some are bold, approaching divers closely, while others remain shy and distant. Some visit cleaning stations during the day, others prefer dawn or dusk. The predictability of manta behavior at cleaning stations has also made these sites popular with ecotourists, generating income for coastal communities and creating incentives for conservation. Octopuses are masters of camouflage, able to change not only their color, but also the texture of their skin, to match their surroundings in less than a second. The octopus's camouflage system is among the most sophisticated in nature. Their skin contains 3 types of specialized cells that work together to create the illusion. Chromatophores are pigment-filled sacs surrounded by muscles. When the muscles contract, the sac expands, displaying its color. When they relax, the sac shrinks, and the color disappears. A single octopus might have millions of chromatophores in its skin, each controlled independently by the nervous system. Beneath the chromatophores lie iridophores, cells containing reflective plates that can produce iridescent blues, greens, and golds. Deeper still are leucophores, which scatter light to produce white coloration. But color change is only part of the story. Octopuses can also alter their skin texture through muscular projections called papillae. By raising these papillae to different heights, an octopus can transform smooth skin into a bumpy, rough surface that mimics coral, rocks, or algae. The transformation happens almost instantaneously. An octopus sitting on smooth sand can suddenly develop spiky protrusions matching nearby coral, then flatten them again moments later when moving to a different background. They accomplish this through specialized cells called chromatophores, iridophores, and leucophores that expand and contract to create patterns and colors. The control system for octopus camouflage is extraordinarily complex. Each chromatophore has its own dedicated neurons controlling the muscles around it, meaning the octopus brain must coordinate millions of individual color cells to create coherent patterns. Researchers discovered that octopuses can create patterns they have never seen before, suggesting they possess an internal library of camouflage options and can generate new combinations. Even more remarkable, octopuses are colorblind. They cannot see the colors they so expertly mimic. Instead, they might perceive colors through their skin itself. Recent research found that octopus skin contains opsins, light-sensitive proteins typically found in eyes, suggesting the skin can detect light independently. This would allow the octopus to sense the color and brightness of its background directly through its skin, and adjust camouflage accordingly, without relying on vision. The speed of color change is astonishing. High-speed cameras reveal that an octopus can transition from one camouflage pattern to a completely different one in as little as 0.2 of a second. This rapid change might startle predators, or help the octopus blend into new surroundings as it moves. Some octopus species have been observed collecting coconut shells and using them as portable shelters, demonstrating advanced problem-solving abilities. Tool use in octopuses was first documented in Indonesia, where veined octopuses were observed collecting discarded coconut shell halves from the seafloor. The octopuses would pick up the shells, tuck them beneath their bodies, and carry them awkward distances across the seafloor, while walking on their remaining arms. Later, when a threat appeared or when the octopus wanted to rest, it would assemble the two shell halves around itself, creating a spherical shelter. This behavior meets the scientific criteria for tool use. The octopus modifies its environment using an external object to achieve a future goal. The behavior requires planning and foresight. The octopus must recognize that the coconut shell, though useless at the moment of collection, might provide protection later. It must expend energy carrying the shells, sometimes stacking multiple shells and moving considerable distances. This investment only makes sense if the octopus anticipates future benefit. Other tool-using behaviors have been documented in octopuses. Some species collect rocks and arrange them as barriers at den entrances. Others have been seen using jellyfish tentacles as weapons, holding the stinging tentacles in their arms, while deterring predators or competitors. Sea turtles navigate across thousands of kilometers of open ocean using Earth's magnetic field, returning to the exact beaches where they were born to lay their eggs. This navigational feat, called natal homing, requires sea turtles to remember the magnetic signature of their birth beach and relocate it years or even decades later. When a sea turtle hatches, it imprints on the unique combination of magnetic field intensity and inclination at that location. The magnetic field varies slightly across Earth's surface, creating a geomagnetic map. Sea turtles can detect these variations and use them for navigation. Female loggerhead turtles born on Florida beaches spend years, sometimes decades, wandering the Atlantic Ocean. They might travel to feeding grounds off the coast of Africa, or drift with currents around the North Atlantic Gyre. But when they reach sexual maturity, they begin the journey home. From thousands of kilometers away, they navigate back to Florida, often to the exact same stretch of beach where they hatched. Researchers discovered this by tagging turtles and tracking their movements. Turtles born on different beaches, separated by only a few kilometers, return to their respective natal beaches with remarkable accuracy. The magnetic field provides the primary navigational cue, but turtles probably also use other senses, including smell, as they approach the coast. Salmon also return to their natal streams to spawn, using a combination of magnetic sensing, smell, and memory of the sun's position. Pacific salmon are born in freshwater streams, spend their adult lives in the ocean, then return to spawn in the exact stream of their birth, often swimming hundreds of kilometers upstream against powerful currents. The journey is so demanding that most salmon die shortly after spawning, their bodies exhausted by the effort. How they navigate back to their home stream has puzzled scientists for decades. Research suggests salmon use a multi-stage navigation system. In the open ocean, they navigate using the Earth's magnetic field and possibly the sun and stars, similar to how birds navigate during migration. As they approach the coast, they begin to recognize the chemical signature of their home river. Rivers carry dissolved minerals, organic compounds, and other chemicals that create a unique smell. Salmon imprint on this smell as juveniles before migrating to sea. Years later, they follow this chemical trail back to their home river. Within the river system, they face another challenge: finding the specific tributary and stream where they hatched. Here they rely on even more specific chemical cues, possibly recognizing pheromones from other salmon in their home stream, or the unique mineral signature of the water flowing over particular rock formations. The mimic octopus can impersonate over 15 different species, including lionfish, sea snakes, and jellyfish by changing shape, color, and behavior. Discovered in Indonesian waters in the 1990s, the mimic octopus has become famous for its incredible shape-shifting abilities. Unlike other octopuses that simply blend into backgrounds, the mimic actively impersonates other creatures, adopting not just their appearance but their movement patterns as well. When threatened by a predator, it assesses which defense might work best and transforms accordingly. If approached by a damselfish, which fears sea snakes, the octopus will change color to black and white stripes, hide 6 of its arms, and undulate the remaining 2 arms, while slithering along the bottom like a sea snake. If approached by a predator that fears lionfish, it will spread its arms wide, display bold stripes, and hover in the water column, mimicking the lionfish's defensive posture. When crossing open sand where it feels exposed, it might bunch its arms and pulse them to mimic a jellyfish drifting through the water. Scientists continue to discover new impersonations. The octopus seems to have an internal library of disguises, and selects the appropriate one based on the situation. This requires remarkable cognitive ability, recognizing predators, knowing which animals those predators fear, and possessing the physical control to execute the chosen impersonation. Parrotfish create mucus cocoons around themselves at night, possibly to mask their scent from predators while they sleep on the reef. Each evening, as darkness falls on the reef, certain parrotfish species prepare for sleep by secreting mucus from glands in their gills. The purpose of this behavior remained mysterious for years. The leading hypothesis suggests the cocoon masks the parrotfish's scent, making it harder for nocturnal predators like moray eels to find them. Moray eels hunt primarily by smell, and tests showed that eels cannot detect parrotfish hidden inside mucus cocoons. However, creating the cocoon requires energy and material that could be used for growth or reproduction. Not all parrotfish species create cocoons, and even within species that do, not all individuals produce them every night. Some researchers suggest the cocoon might also protect against parasites, creating a physical barrier that prevents parasitic isopods from attaching to the fish. Others propose it might help maintain moisture around the gills, or protect against predators that hunt by touch in the darkness. Scientists estimate that we have discovered and named only about 10% of all species living in the ocean. The ocean covers more than 70% of Earth's surface, yet remains one of the least explored environments on our planet. We have better maps of the surface of Mars than we do of the ocean floor. The deep ocean in particular remains almost entirely unexplored, with fewer people having visited the deepest parts of the ocean than have traveled to space. Current estimates suggest the ocean contains between 700,000 and 1 million species, but only around 250,000 have been formally described and named by scientists. This means hundreds of thousands of species remain unknown to science. Every year, researchers discover and describe thousands of new marine species, from microscopic plankton to large fish. The rate of discovery shows no signs of slowing, suggesting that we have barely scratched the surface of ocean biodiversity. The deep ocean likely harbors the greatest number of unknown species. Each time a submersible descends to unexplored depths, or visits a new location, it encounters species never before seen by humans. Some of these creatures are so different from known organisms that they require new families or orders to classify them properly. New species are discovered regularly during deep-sea explorations, from bizarre fish to creatures that challenge our understanding of how life can exist. The creatures discovered in the deep ocean often seem alien. adapted to conditions so extreme that scientists once believed complex life could not exist there. In recent decades, expeditions have discovered fish with transparent heads, squid with elbows in their tentacles, and worms that bore into whale bones. In 2014, researchers exploring seamounts off the coast of Australia discovered over 100 new species in a single expedition, including bizarre-looking fish and invertebrates that looked like something from science fiction. Near hydrothermal vents, scientists found entire communities of organisms unknown to science, including giant tube worms 2 meters long that have no mouth or digestive system, and survive through symbiotic bacteria living in their tissues. These discoveries challenge fundamental assumptions about biology. Some deep-sea organisms survive without sunlight, deriving all their energy from chemicals. Others withstand pressures that would crush most life forms. Some fish produce antifreeze proteins to prevent their blood from freezing in near-zero temperatures. The more we explore, the more we realize that life is far more adaptable and diverse than we previously imagined. The ocean produces over half of Earth's oxygen, primarily from phytoplankton, microscopic plants drifting near the surface. When people think about oxygen production, they often imagine vast forests with trees, converting carbon dioxide into oxygen through photosynthesis. While forests do produce significant oxygen, the ocean's contribution is even greater. Tiny phytoplankton, so small that millions can fit in a single drop of water, collectively perform more photosynthesis than all terrestrial plants combined. These microscopic organisms include various species of algae, diatoms, and cyanobacteria. They drift in the sunlit surface waters, using solar energy to convert carbon dioxide and water into sugars, releasing oxygen as a byproduct. The oxygen dissolves into the seawater, and much of it eventually enters the atmosphere, where it becomes available for animals to breathe. Scientists estimate that phytoplankton produce between 50 and 80% of Earth's oxygen, with the exact percentage varying by season and location. Every second breath you take comes from the ocean. Without phytoplankton, atmospheric oxygen levels would plummet, making the planet uninhabitable for most animals. These microscopic organisms have been producing oxygen for billions of years, gradually transforming Earth's atmosphere from an oxygen-poor environment to the oxygen-rich one we know today. These tiny organisms form the base of the ocean food web, and their seasonal blooms can be seen from space as changes in ocean color. Phytoplankton populations fluctuate dramatically throughout the year in response to changing conditions. In temperate and polar regions, spring brings longer days and increased sunlight. Nutrients that accumulated in surface waters during winter are still available, having not yet been depleted. These conditions trigger massive phytoplankton blooms where populations explode, sometimes increasing 1,000-fold within weeks. The blooms are so dense that they change the color of the ocean. Satellites equipped with special sensors can detect these blooms from space, watching them develop, spread, and eventually decline. The color changes provide information about phytoplankton abundance and type. Blue water contains few phytoplankton. Green water indicates high phytoplankton density. Some species create red or brown blooms, sometimes called red tides, which can be toxic to other marine life. These blooms are crucial to ocean ecosystems. Zooplankton, tiny animals that feed on phytoplankton, increase their populations in response to the abundance of food. Small fish that eat zooplankton also increase. Larger fish, marine mammals, and seabirds follow, all benefiting from the seasonal pulse of productivity that begins with these microscopic plants. The ocean absorbs about 30% of carbon dioxide released into the atmosphere, helping to moderate climate change but becoming more acidic in the process. The ocean acts as a massive carbon sink, absorbing carbon dioxide from the atmosphere through gas exchange at the surface. When carbon dioxide dissolves in seawater, it forms carbonic acid, which then breaks down into bicarbonate and carbonate ions. This process helps remove carbon dioxide from the atmosphere, slowing the rate of climate change. Without the ocean's absorption, atmospheric carbon dioxide levels would be much higher than they currently are, and global warming would be progressing faster. However, this service comes at a cost to the ocean itself. The carbonic acid formed when carbon dioxide dissolves in seawater lowers the pH, making the ocean more acidic. Since the beginning of the Industrial Revolution, ocean pH has dropped by about 0.1 units, representing a 30% increase in acidity. This change might seem small, but it has significant effects on marine life. Many organisms, including corals, mollusks, and some plankton species, build shells or skeletons from calcium carbonate. As ocean acidity increases, it becomes harder for these organisms to maintain their calcium carbonate structures, which can begin to dissolve in increasingly acidic water. Ocean acidification is changing the chemistry of seawater, making it harder for creatures with calcium carbonate shells and skeletons to survive. The effects of ocean acidification are already being observed in marine ecosystems around the world. Pteropods, small swimming snails that form an important food source for fish and whales, show shell dissolution in increasingly acidic waters. Young oysters have difficulty forming shells in hatcheries along the Pacific coast, where upwelling brings naturally acidic deep water to the surface, a problem exacerbated by additional acidification from atmospheric carbon dioxide. Coral reefs face a double threat from warming and acidification. Warmer water causes bleaching, while acidification makes it harder for corals to build and maintain their calcium carbonate skeletons. Some corals grow more slowly in acidic water. Others show more fragile skeletons that break easily in storms. Laboratory experiments suggest that if acidification continues at current rates, by the end of this century, some areas of the ocean might become corrosive to calcium carbonate, causing shells and skeletons to dissolve faster than organisms can build them. This would devastate coral reefs and threaten any organism that depends on calcium carbonate structures. The impacts would cascade through food webs, affecting species far removed from the initial changes. Despite covering most of Earth's surface, we have better maps of Mars and the Moon than we do of the ocean floor. Space exploration has captured human imagination for decades, leading to detailed mapping of planetary surfaces millions of kilometers away. We have comprehensive maps of Mars, showing features as small as a few meters across. The Moon's surface has been mapped in similar detail. Yet right here on Earth, beneath the waves, vast areas of the seafloor remain unmapped, or mapped only at very low resolution. Traditional sonar mapping requires ships to sail back and forth across the ocean, a slow and expensive process. Most of the ocean floor has been mapped using satellites that measure subtle variations in the height of the ocean surface. These variations correspond to the topography of the seafloor beneath, as underwater mountains create slight bulges in the ocean surface above them. While this technique provides a basic map, its resolution is limited to features larger than about 5 kilometers across. Everything smaller remains invisible. Recent initiatives aim to map the entire ocean floor at high resolution by 2030, using a combination of ships, autonomous underwater vehicles, and new technologies. This mapping effort will reveal underwater mountain ranges, seamounts, canyons, and other features we currently know nothing about, New technologies, including underwater drones, advanced sonar, and deep-sea submersibles, are allowing us to explore deeper than ever before. Ocean exploration technology has advanced dramatically in recent decades. Remotely operated vehicles, or ROVs, can descend to depths that would crush human-occupied submersibles. These robots, controlled from ships on the surface through fiber optic cables, can spend hours on the seafloor collecting samples, taking high-definition video, and conducting experiments. Autonomous underwater vehicles, or AUVs, operate without tethers, following pre-programmed routes, or using artificial intelligence to make decisions independently. They can map large areas of the seafloor, or search for specific features like hydrothermal vents. Human-occupied submersibles continue to improve as well. Modern deep-sea submersibles can withstand pressures at the deepest points in the ocean, and remain submerged for extended periods. They have increasingly sophisticated sensor packages, including cameras capable of detecting bioluminescence, and chemical sensors that can identify different water masses. Advanced sonar systems can create three-dimensional maps of the seafloor with centimeter-scale resolution. Environmental DNA techniques allow scientists to identify species present in water samples without seeing the organisms themselves, revealing biodiversity in areas that appear empty. These tools are transforming our ability to explore and understand the ocean. Each new expedition to the deep ocean reveals ecosystems and creatures never before seen, reminding us how much remains unknown. In 2012, filmmaker James Cameron descended to Challenger Deep, the deepest point in the Mariana Trench, at nearly 11,000 meters below the surface. In complete darkness and under crushing pressure, his cameras captured sea cucumbers and amphipods going about their lives. The find confirmed that life exists even at the absolute limits of the ocean's depths. In 2018, scientists exploring seamounts in the Atlantic Ocean discovered a massive deep-sea coral reef system, extending for nearly 600 kilometers. This reef, despite being larger than any coral reef system in the Caribbean, was completely unknown until sonar mapping revealed its presence. In Antarctica, researchers drilled through half a kilometer of ice and discovered a community of organisms living in the perpetual darkness beneath the Ross Ice Shelf, hundreds of kilometers from open water and any obvious food source. Each of these discoveries challenges our assumptions about where life can exist and how ecosystems function. They remind us that the ocean holds countless surprises, from individual species to entire ecosystems, all waiting to be discovered. The ocean continues to hold its mysteries close, a vast frontier of discovery waiting beneath the waves, calling us to explore, understand, and protect it. After centuries of ocean exploration, we stand at an interesting moment in history. We know enough about the ocean to understand its critical importance to Earth's climate, biodiversity, and the survival of life on our planet. We have discovered remarkable creatures and ecosystems that expand our understanding of biology and evolution. Yet we also recognize how much remains unknown. Vast areas of the ocean have never been explored. Countless species await discovery. Fundamental questions about ocean circulation, the role of marine microbes in global cycles, and the impacts of human activities on ocean ecosystems remain unanswered. The ocean is not just a place of scientific curiosity, but a critical life support system for our planet. It regulates climate, produces oxygen, provides food for billions of people, and supports biodiversity that rivals or exceeds terrestrial ecosystems. As we continue to explore the ocean, we must also work to protect it. The mysteries waiting in the deep are not just scientific puzzles, but represent the natural heritage of our planet, treasures that deserve to be preserved for future generations to discover and wonder at. And so our journey beneath the waves comes to a close. The ocean still holds its secrets in the deep, where bioluminescent creatures glow in the darkness, and life thrives in ways we are only beginning to understand. From the sunlit surface to the darkest trenches, from the smallest plankton to the largest whales, the ocean reminds us that our planet is full of wonder. The mysteries of the deep remain, waiting quietly beneath the surface, for you to return. Thank you for diving into the ocean with nightly lore, sweet dreams, and may the gentle rhythm of the waves carry you to rest. Until next time, good night.